Okay, thanks a lot, Sotirios, for this nice introduction. I want to thank the organizers for giving me an opportunity to talk about a very old paper of mine, two very old papers of mine, which were jointly written with David Nualart and Sanz-Sol&acute from Barcelona. Okay, we worked indeed on time reversal for diffusion processes, and for us, it kind of was a closed subject because we kind of proved necessary and sufficient conditions. So we went away from this topic. And last year, I encountered Jocelyn Garnier, who told me, by the way, you know that time reversal is being used in artificial intelligence. I was stunned. And then so when Sotirios invited me, I thought, aha, I know. He wants me to talk about time reversal. But okay, I feel like a bit an alien in this conference, to be honest. All right, so let's proceed. Okay, so let me describe vaguely the problem. I think it's a hybrid audience, so I'll be very basic to start with. So we have a WT, which is a multidimensional Brownian motion on some probability space. X0, which is independent of this Brownian motion, and we start with, for a probability very well-known model, namely a diffusion process. So we have a diffusion coefficient, sigma, which acts both on time and space and going to matrices, and a drift coefficient. I'm going to suppose that they are globally Lipschitz and have a linear growth condition. This is a classical setting, right? And then I have a strong solution to this stochastic differential equation. Namely, I start with this given Brownian motion, and I have a trajectorial solution. Fine. Let me denote by A, something which is be crucial in the moment, the diffusion matrix, that's sigma, sigma star. And let me focus on one thing, a second order differential operator, which will be crucial in what's going to follow, namely the generator of the diffusion. Okay, so maybe most of you know, but maybe some people need to be refreshed about what this means. So it's a second order operator acting on some regular enough functions. Here, I'm not going to be fancy about assumptions. I support it's compact supported, taking very smooth if you like. That's not really my problem. Okay, so you look at the second order differential operator, you have the diffusion matrix acting on the second order derivatives of F, and then the drift coefficient acting on the first diffusion coefficients. And the key point is the following. If you use Ito's formula, it's clear that if you look at f of xt minus f of x0 minus the time integral of the generator acting on f at time xs, you remove this deterministic time interval, you get a continuous marking. It's just a leftover what you missed from Ito's from. Okay, fine. Now the question arises is what's going on if we reverse time? It might look first like a strange idea. I am not going to go backwards in a trajectorial way, of course. I'm going to go backward in distribution, right? So let me denote by x bar t, x1 minus t. It's a Markov process, which is extremely handy. But the question which arises is it again a diffusion? Can I find an operator? Can I find a diffusion matrix? Can I find a drift coefficient? So that if I look at m bar f, which is f of x bar t minus f bar 0, minus the time integral of the generator L bar, which ought to be associated with x bar, can I have a martingale? All right, and if that's the case, what are the drift and diffusion coefficients? Okay. All right, then it's more or less the same as looking at a weak solution. I'll go back to this in a moment. That means finding not only the process, but also an underlying Brownian motion that's going to drive this reverse time process. All right, so now that's a good question. I think it's going back long ago. I think it started with Schrödinger and Nelson in the 30s of last century, of course. And the problem is that the answer is no in general. You need conditions for this to hold, but under some conditions it does work, okay? So I think I'm just going to skip this slide because I'm not going to explain you how you use time reversal. Let me just say, waving hands, that in my okay, in the very few papers I downloaded last week, because I mean, I have absolutely no knowledge of artificial intelligence, let me repeat. I found that there are kind of two frameworks where this is being used. On one hand, finite dimensional processes, that in most cases I've seen is some kind of Steiner-Lundbeck-like processes, namely that the diffusion coefficient does not depend on the process. And I can understand why, I guess, because I mean, at some point you need to, and the drift coefficient is linear, which means that it's some kind of Steiner-Lundbeck-like process, which means that you know that it's Gaussian and therefore you know what the density looks like, which turns out to be very important in what is going to follow. That much I can go with. And interestingly enough, there is also an infinite dimensional version, which seems to be fashionable right now. And we have both results in the finite and infinite dimensional cases. Okay, so now let me comment about non-results. I mean, there are quite a few, but let me just quote very old results. As I mentioned, it started with Schrödinger and Nelson. They could not really give, I think, the proper diffusion coefficient and the proper drift coefficient, but they were interested in this kind of problem. And the reason why is that I think they were interested in statistical mechanics and Gibbs measures. It was in physics. Okay, and then I think in the book, I forgot the year, but I mean, the person showed that it's not always the case. X bar T need not be a diffusion. So there are some conditions to be imposed for this to hold. Then let me quote two papers. The first paper by Anderson, which I've seen is quoted by everyone in this community. I think it must have some 10,000, 100,000 citations, which appeared in 1982. So the idea, I think he should be given credit because he had a nice idea. He thought, okay, let's use forward and backward chromograph equation. That means there is a link between PDEs and either the density or something. And also he understood that the density of the direct process would be involved in the drift of the reverse diffusion. Unfortunately, he did not give any justification for his backward chromograph equation. He went a bit off and his drift coefficient is wrong. The drift coefficient is the opposite of what it should. All right, then a few years later, Hussmann and Pardue worked again. Okay, oh, that's an interesting idea, but let's try to prove it. So they came with sufficient conditions. They give the correct drift, and in the reverse sign from Anderson's drift. And they give a sufficient condition for the backward diffusion to be the backward process to be a diffusion process. They extended to local Lipschitz coefficients, and they also, interestingly enough, give some information about the driving inner process, that driving the reverse process. Okay, so basically this was a forward and backward chromograph equation. There were two PDEs associated with diffusion, which I guess at that time was kind of natural approach, which I would say now is a bit vintage, in my opinion. Okay, then let me, okay, all these papers by the, okay, several papers, 86, 86, 86, and on next slide, again, 86. So that year, I mean, it was a tremendous activity around this problem. So there are paper by Fulmer who had another point of view. He used entropy and enlargement of filtrations. Entropy, I've seen yesterday, it's used by some of you, but I'm not going to discuss anything about this entropy approach, okay? I didn't have time to go back to this paper on entropy. All right, and then Pardue more said, okay, enlargement of filtrations, that's good, that's something I know. So he also produced a paper about that. And then we came in 1989, so that's 35 years ago. And at that time, we thought we were inspired, of course, by these previous papers, especially by the one by Hussmann and Pardue. And we thought, can we provide a purely probabilistic approach to this time reversal? And the answer was yes, using Malien calculus. Okay, you might be frightened by the word because Malien calculus, oops, it's something horribly technical. It's something which is used to prove that the existence of double density, there's this under condition. It's not for me. I am trying to convince you that, no, it's for you. It's not that complicated. I mean, the tools that I'm going to use later on are quite simple. Okay, so what we did is that, in a way, we gave a kind of necessary and sufficient condition. It's different from what Haussmann and Pardoux obtained. And in a way, I tend to believe that's kind of optimal. In a way, it's necessary, okay? We also could extend to locally Lipschitz coefficients. All right, then let's go to infinite dimension. Let's go backward in time. Again, in 86, there was a paper by Fulmer and Wacol-Binger. I think there was also a paper by Deutschel and Fulmer at that time, more or less at that time. But I mean, this paper I didn't look at. They dealt with infinite dimensional stochastic processes. And again, using entropy, which was the tool that Haussmann used in his first paper, they gave sufficient condition for its bounty to have a density. Their covariance matrix in infinite dimension was identity, let's say. It was very, very particular. And for them, I guess at that time, it was again connected with Gibbs measures. And an advantage, I think, is that there was also a link with invariant measure that I should have mentioned in the previous slide, that they could afford with this entropy method to go to non-Markov processes, which is a bit a mystery to me because the reverse diffusion is Markov anyway. And then we came, since we had gone through the problem in finite dimension, we said, why don't we do that in infinite dimension? So we more or less did the same. It's much more technical. Okay. All right, so what's the aim of the talk? I guess for some of you, time reversal is some kind of black box. So the aim of the game is open the box, look at what's inside, try to understand why this black box is operating and how this black box is operating. Okay, so first things first, let's go to finite dimensional case using the martingale problem approach that you've seen with Istvan György, I think, in the first week of this event. Give the hint of the proof. Why is this condition, which is going to pop out a moment, necessary, kind of necessary? The proof is very easy. It just uses Ito's formula. So it's kind of standard proof, straightforward proof. But it's going to be a training because we'll see what are kind of ideas being used. And then we are going to be able to transpose this proof for the sufficient condition. And there, Malyavet calculus is going to pop out. We'll see how. Then, if time allows, I'll go to the infinite dimensional setting, no proof. Again, just give you a rough idea of what kind of results were obtained. And then, because Sotiros asked me to do so, if time allows again, I will go back to the Haussmann and Pardoux approach using PD techniques, absolutely no proof, and give you some hint of what the reverse inner process looks like, and more or less what the idea is. Okay, so now let's proceed. Okay, let's go back to the martingale problem. So we start with the diffusion process. Again, I remind you what the generator looks like, and the martingale, which is associated with that, provided that F is very smooth bounded, all the assumptions you need in order to have a martingale. Right, now let me formulate formally what's a martingale problem. Martingale problem associated with the generator, that's, okay, you take the canonical space. That means a set of continuous functions from 0, 1 to Rd. You endow it with Wild sub-sigma field, sorry. And then the question arises, can you find a probability on that space, on that canonical space, in such a way that if you look at, f of yt minus f of y0 minus y, I'm sorry, I should say that y, this is the map from the continuous functions, maps it to what is going on at time t, kind of canonical process. And you want to find a probability so that this is a martingale, a continuous local, okay, I said local martingale because I did not put any boundness requirement, but forget about it, take it compactly supported, then it's going to be a nice martingale. Fine. Well, okay, there is a technical problem which arises. Strictly speaking, you have enlarged the filtration because you have to add these null sets of the probability you're looking for. And then it turns out to be equivalent with the weak solution, namely, again, something I mentioned a moment ago, finding a pair, Brownian motion and process, so that everything is fine. But of course, I am not working anymore with a given Brownian motion. I have some Brownian motion, and theoretically speaking, I don't care what it looks like. But for you, of course, problem might be different. Okay. Now, let me state the necessary and sufficient condition we obtained. So WT, business as usual, sigma and B are globally Lipschitz. And now the main assumption I'm going to make is that very crucial assumption is that at time t strictly positive, my direct process must have a density. And this was already observed by Anderson, by the way. He already observed that in order at some point he needed that. So it's not artificial, it's no artificial assumption. All right, so now suppose that, I don't know, can I point out black? I don't know, maybe black is not something wise to do. Here is some kind of integrability condition. You might not care about it, but as a theoretical person, I might. So you start with a strictly positive time t0 on a compact, not a compact, I think it should be an open, whatever, something bounded in it. Domain in the space variable, and you look at, okay, whenever there will be an index down below and an index on top, that's J here, that means I am summing, right? It's kind of standard convention of notation. So I'm requiring that the time and space integral of the absolute value of the norm, let's say, of this sum over J is finite. This sum mixes on one hand the diffusion coefficient and the other hand the density of the forward process. Okay, then what's going on is that the reverse process is a diffusion process, and I can identify its generator. The diffusion matrix is just the same, and the drift coefficient is related with the previous drift coefficient, but this thing for which I made an assumption is popping out. And it's popping out in a kind of strange way because you have to divide by the density and take the gradient of the product of the diffusion matrix with the density. And of course, we have to understand what we mean by, if I may not divide by 0, right? So in case that my density 0 vanishes, then my notation means that the whole second term in the right-hand side vanishes. And you see that strangely enough, it's not really a correct, it's indeed a correction of the drift coefficient, but it's correction of the opposite of the drift coefficient. Okay, so that's kind of a sufficient condition. And now let me state some kind of necessary condition. So let's make some assumption, integrability assumption again with the, so to 2 A bar and B bar, which are measurable, so that this integrability condition holds. It's respect to the density of the direct process. So I'm given these processes and I have L bar T, and I suppose now that X bar T, my time reverse process, is a martingale problem associated with L bar. The question which arises is the following: can I identify the coefficients once I'm given this information on one hand? And the answer is yes. It's just business as usual, exactly what I had in the previous slide, right? And on top of that, the local integrability condition are required for the sufficient condition is satisfied. Now, the second point is kind of clear. Why? Okay, I have this integrability assumption I impose at the first blue line on top of my theorem, right? It's definitely satisfied if I replace A bar by A and B bar by B, just because I have some kind of local integrability property for my direct process. And now if you look at the relationship between B bar and B, well, you look at the integral of the absolute value of B bar is finite, you know that the absolute value of B is finite, and of course the difference, no choice, that's got to be finite as well. So of course I'm cheating a little bit because I'm making this kind of integrability assumption to claim that it's a necessary condition. Okay. All right, now let's move to the proofs, because I discussed with Soterios, and if you are unhappy with the proof, don't blame him, don't blame me, blame him. So I'm going to give you, yeah.
Is there, of course, the condition is difficult to check because you have a condition of PT of X, so you need an integration. Is there a condition which can be really expressed in terms of the coefficient of the diffusion coefficient?
Yes, if time allows, I'll show you Hosman and Pardue. They gave a sufficient condition, but it's not that different from this one, to be honest. It's pretty much alike. Oh no, it has PT. Hold on. I can replace the diffusion matrix by the diffusion coefficient. I can slightly rephrase the condition, but PT, forget it. You have got to deal with it.
It's in the martingale.
Pardon?
to achieve the martingale.
Okay, we'll see how it comes into, okay, in the proof, you will see how it pops out and how it is kind of unavoidable, I would say. Okay, so, all right, so let's go to the first easy proof, which I told you, it's just based on Ito's formula. Just based on very, very simple stochastic analysis. Okay, so let me not be confused with indices. So let me suppose that everything is one-dimensional, just to try to focus on the main ideas of the proof. All right, so let me rewrite my martingale problem with L bar P, X bar and X bar T, X bar S, and my reverse operator. So that's the first natural way to write it. And now you make a kind of tricky change of variable, and on top of that, you re-exchange variables so that S be always less than or equal to T. Because I want to go from the X bar process to my given process, my strong solution, because that I can work with my strong solution. So you do that, and at the end of the day, you get to the last line. That means that now instead of conditioning, maybe the four last line, instead of conditioning with XS, using the fact that you have a Markov process, you condition with X bar T. And conditioning with S bar S, sorry. So conditioning with X tilde T with this change of variable means that if I put everything back in the right order, that means S is less than or equal to T, I'm going to have a condition expectation with respect to GT, to FT, sorry. That means that I'm now going to condition with respect to X capital T, which is a bit strange. I'm going to condition with respect to the future instead of conditioning with respect to the past. In a way, I mean, you are reversing time, so there's a price to pay. Okay, fine. Now, look at the right-hand side. Now, here, I know that L bar T is that X bar is a diffusion process, and I know that it's associated with L bar. So the idea is that I can do whatever I like with the time in S and T. So let me S to be T minus H, right? Why not? And let's H goes to 0. And if I do that, using Lebesgue's differentiation theorem in the right-hand side, it's clear also L bar, that's minus L of, I'm sorry, L tilde, that's minus L bar of 1 minus theta. It's a bit confusing. You have this change of sign which pops in day out. So you here just look at this time integral on a very small time interval, T minus HT. You divide by H, you let H go to 0, and the Lebesgue differentiation theorem tells you that for almost every T, you get what's inside of your interval at time T. That means that you get what I wrote on the last line. That's fine. That's fine. I could use Lebesgue's differentiation theorem for the right-hand side. Now I have got to do that for the left-hand side. Okay. Now it doesn't look so great because, I mean, there is no time integral, right? So let me force a time integral. I apply Ito's formula. Now in my left-hand side, because I've chosen S to be T minus H, I'm going to apply Ito's formula. And two things are going to pop out. One deterministic integral, that's great. One stochastic integral, that's not so great, but we'll see how to deal with it. Okay, so as I mentioned, we have two terms in the after applying Ito's formula for F. So we have some deterministic integral, which I denoted by T1. That's fine. You are going to use Lebesgue's differentiation theorem, and it's going to give you what the limit. Great. And now you are facing the stochastic integral. All right, then something has got to be done about it. I cannot leave it this way. I cannot use Lebesgue's differentiation theorem as a stochastic integral. So what the idea? The idea is to force the difference G of xt minus G of xt minus H. Why is that interesting? If I have G of xt minus H, it's ft minus H measurable, and therefore it's independent of the stochastic integral. It's not, maybe not independent, but at least it's uncorrelated. That means that the expected value of the first thing I'm supposed to deal with G of xt. If I replace G of xt by G of xt minus H, forget it, it's 0. And therefore I can force this difference. If I can force this difference, let's apply again Ito's formula. Okay, so another time integral is going to pop out. for both the stochastic and the deterministic integral. So we have two terms, right? The two terms I denoted T21 and T22. T21, that's the bad term. Well, not so bad, we'll see. 222, again, it's not such a, it's a good term for the following reason. What's going on? You have now to divide this guy by h. Let h go to 0 and hope for the best. What is the order of the two terms I have? I have a stochastic integral. If I look at p moments, its order is h/2, right? And I have a deterministic integral. If my deterministic integral is bounded, that's well, because I have something bounded on a time interval of length h. That means that if I look at T22, the order of T22, that's h to the 3/2, kind of, waving hands. But I mean, it can be made rigorous. You divide by h, you can forget about it. Okay, great. I've got rid of one of my terms. Now what is going on with the next one? But the next one is not so bad, because that's kind of isoisometry. It's a product of two stochastic integrals. So you may have seen that the isometry tells you that the square of the h1, the expected value of the square of a stochastic integral is equal to the expected value of the time integral of its, the square of its, what's inside. And okay, then it's the square, you take the just linearize that and you get, you hand that whenever you encounter a product of these two stochastic integrals, that's fine. You can go back to a deterministic integral, one deterministic integral with the product of the two integrals. So let's do that. Okay, fine. Then I am back to my favorite situation. I can use Lebesgue differentiation theorem and focus on what's inside, but there's still a problem. What's the problem? The problem is that I've used Ito's formula for G, right? So I end up with something which is nice, except that I have the gradient. And I don't want that, because at the end of the day, I want to identify something where in my expected value, I had G, not the gradient of G. So I've got to get rid of this G, of this gradient. I have to replace gradient of G by G. And that's where the density is going to come in, whether you like it or not. You have got to force the density. Otherwise, here it's a hopeless situation. Okay, so for the density and use integration by parts, classical integration by parts on RD. And then, of course, that's what I wanted. I wanted to go back to x, g of x, right? But of course, the bad news is now I have the gradient of the product of three guys. F, a gradient of F, A, and P. Okay, if I think back to what my operator looked like, I want to have gradient of F and second derivative of F, that's fine. So let me use integration by parts in order to have these two things pop out, right? So I have here the gradient of product of three terms. I'm just isolating F and putting the two other things together. That's how I end up with G multiplied by something in brackets, which has both the diffusion matrix multiplied by the density multiplied by the square. Okay. I hope I did. No, that's fine. I'm sorry. I was worried about signs because since Anderson made an error, no, the sign, it's fine. Because I use integration by parts, minus sign pops out, and I'm just telling you what the derivative of a product is. So there is no problem. Okay, now we're almost done. Put everything together, collect everything. You end up with this identity. Okay, fine. Now, interestingly enough, in the right-hand side, you have some compensation in the diffusion matrix. One of the terms came out of applying Lebesgue differentiation theorem with G, with the Ito's formula. It gave you 1/2, and there's -1, which is popping out from this integration by parts business. Okay, and then suppose that f of x is x. Okay, I suppose that it was compactly supported. Never mind. Intuitively speaking, suppose that f of x is x. Second derivative, forget it. You just identify some coefficients and it tells you what d bar should look like. And it should look like the way I presented in my previous slides. And then once you have identified the drift coefficient, it's easy to identify the diffusion coefficient because you just suppose that f of x is x. Okay. So I think it's kind of trivial, but like simple, kind of simple proof. So the crux of the matter was that I could choose, in the very first martingale problem I stated, I could choose S to be T minus H, and I could use Ito's formula. Okay, now I want to go backwards. I want to start with some integrability assumption, and I want to prove that my reverse process is a diffusion. So I want to prove that I have a martingale problem and identify the coefficients. And then some ideas will be the same, but a technical problem is going to arise. That's how are we going to deal with the stochastic integral? All right, so sufficient condition. A new tool is going definitely to be needed. So business as usual, I suppose that my local integrability condition is satisfied. I said that L tilde U is minus L of minus minus U. And now I want to prove this identity. That's completely different. I'm not given this identity to identify the coefficients. Okay, so now I am again going to use Lebesgue's differentiation theorem, but in a quite different way. Instead of getting close to T, I'm going to say that T is fixed and I'm going to get close to S. That means that I'm going to look at the difference XS minus XF minus H. And if I'm supposed to get a martingale problem, then something of that kind should be true. All right, so that's true for, okay, it's just a difference of those two. I mean, you just look algebra and you see that what I'm writing is true. And again, the right-hand side is well, because I just have to pass the limit in the deterministic integral using Lebesgue's differentiation, right? Okay, fine. Now, again, Ito's formula, no choice. So, but now I'm using Ito's formula for f of xs minus f of x minus h. Okay. So deterministic integral, that's fine. I can use the Lebesgue differentiation theorem and I'll be through. But now what shall I do with this other guy? I have a stochastic integral. And then Malevin calculus comes into the scenery. So the Malevin calculus, okay, it's an integration by parts formula of Malevin calculus I'm going to use. And I'm going to give you some information as Sotirios asked me about Malevin calculus, but it's kind of very handing with information, 3 slides, trying to convince you that Malevin calculus is tailored to face this situation. So what's going on? I have the product of some random variable multiplied by, oh, okay, I'm sorry. Okay, I hope I'll be forgiven. G of t G of t of course should be outside of the stochastic integral and not inside of the stochastic integral because it's not adapted. It's okay. So what I should have written is expected value of G of xt multiplied by some stochastic integral. And now what I want to do is turn the stochastic integral into a deterministic integral. Okay. And now, okay, all right, let me just give you a few, I think, nice references. I mean, tremendous work has been done on this subject. If you're an analyst, you might like Stokes' lecture notes. He's given, okay, very good insight of the Hermander condition, but I'm not going to do that, although it would be interested to find sufficient conditions for the density to exist. And I'm going to more or less focus on what's going on by David Nualart. So he wrote a book. The first edition, I think, was in '95, and the latest edition was more recent about Malevin calculus and related topics. And if you just want to know, you're not that much interested in everything which is in this book, you can have a look on some lecture notes about the Saint-Flour Probability School, which was held in '95, where he gives basic results and it does not go into too many details. Okay, so what's the idea? I have stochastic integral. I want to have some derivative that goes together with it. And I want to have some duality between the stochastic integral and the Malevin derivative. Okay. of course, I mean, on top of that, you have many, many more applications, but the only thing I'm really interested in right now is to understand this integration by part from this problem. Okay, so as I mentioned, it's a duality between the derivative and integration. So let me now, from scratch, define what derivative looks like. Okay. All right, so, all right, I'm going to rush through that because I want to go to the proof where it's used. All right, so you start with a Gaussian process. So let's introduce the common Martin space. So again, it's an L-dimension Brownian notion. I'm doing it in kind of abstract setting, more general setting. It's the set of upper bound integrals of a square integrable function. That's, in a way, it's an H1 function for the time variable, but for the space variable. All right, now let me for an element H in, okay, this of course is isometric with L2. You can make an isometry between the upper bound integral and one in the integral inside. All right, now define for an element H of H dot of capital H, what I'm going to call W of H. That's just a sum of stochastic integrals, which are Gaussian processes, because I mean, I'm taking the stochastic integral of a deterministic function, right? Okay, great. Now let me introduce a set that I'm going to call smooth random variables. So they are the smooth function of W at for various elements of my common Martin space. And let me define what I want to denote by the derivative. Well, I just take the derivative, all gradients of the function, depending on the index where I am, and I multiply by hi. Why not? So that's, of course, that's going to give me an h-valued function. Okay. Let me give you two examples so that you can more or less have a more clear idea of what's going on. So suppose that L is 1, I just have f of is W of H, and the derivative of W of H as H. And in the particular case that H is the indicator function of 0t, I get Wt as W of H, and my derivative is integrated in integrator function of 0t of S. What does that mean? That means that the S does not see the future in a way. The S of Wt vanishes for not enough S. And that's going to be important. Okay. Now, integration by parts. Very basic. Very basic. I have very smooth random variables. And I am going to tell you something which is more or less what I was facing a moment ago, except that H of S was not necessarily some kind of deterministic term. But in the right-hand side, I have expected value of some random variables multiplied by the stochastic integral. And what's going on in the left right term, I have expected value of a deterministic integral. But the price to pay is that the derivative, the Malyaver derivative of S is showing up. Okay. Okay, I'm not going, I think I skip the proof. The proof is very simple, and it's indeed based on integration by parts on all right. Okay. It's improved now. Okay, you have a concept of derivative. Well, then you make Sobolev spaces. You can raise the order of the derivative as much as you like. You take moments, and then, okay, what kind of properties does a derivative have? Generally, okay, sure, it's fine. We have the chain rule. That means that if we have a smooth enough function, we can define we can say that the derivative of, oh, I'm sorry. I should say that, of course, the idea of understanding these Sobolev spaces is not only to be able to take the Malyaver derivative of a smooth random variable, but the Malyaver derivative of something which is much more general. Okay. So chain rule is kind of natural. Okay. That's the important property. Now this is the adjoint of D. So here I'm going kind of backwards. I told you, I tried to sell you the Malyaver derivative, telling you it's the adjoint of the stochastic integral. Well, yes and no, because in fact, what's the proper way to think at things is that to take the Malyaver derivative and to look at the adjoint operator. That's the so-called score-out integral. It enables you to integrate something which is not necessarily adapted. But what's important is that provided that U is adapted, you get back to the two integral. On one hand, and also it's a domain. I mean, the domain of this operator, it contains D12 and D12, that's a kind of Sobolev space you can associate with your Malyaver derivative. at least when I used to work on Malevin calculus, which is not the case for a long time, the domain of the precise domain of delta was unknown, but at least it contains D1. All right, now integration by parts. Now that the true formula, the true general formula, which tells you that in the left-hand side, you have f times your square root integral, and then the right-hand side, you have some inner product in h, which is the time integral. Okay, and now, okay, I pointed out a moment ago that the derivative of W2 was vanishing, provided that if S was larger than T. And that's exactly the same property for adapted processes. Okay, and now, okay, we have to do something unpleasant. Can we commute the derivative and deterministic and stochastic integral? Of course, that's a natural question. For deterministic, that's fine. Okay, the Malevin derivative. So here I'm denoting the alpha t because I might be taking the derivative with respect to the W alpha component of my multidimensional process. So alpha is an index that varies from 1 to n. So the alpha, that's kind of Malevin derivative in the direction of W alpha. Okay. You take this derivative of a deterministic integral. Well, in the right-hand side, you get a sum. So then the chain rule. Derivative of B of the drift coefficient multiplied by the Malevin derivative of the J's component of your process. Fine. Now what's going on if I start having the Malevin derivative of stochastic integral? It's not going to be that easy anymore. And in fact, that's why I put two indices here. If you look at the Malevin derivative of stochastic integral driven by W beta, and if alpha is different from beta, it's as if it were deterministic. But in the case that you take the Malevin derivative in the direction of W alpha and your stochastic integral is taken with respect to W alpha, another term is popping out, namely the sigma alpha, the integral with in the direction alpha. All right, now we are prepared to go to the proof of the sufficient condition. All right, so let me go back to what I stopped a moment ago. Namely, I have got to deal with G of xt multiplied by stochastic integral. Okay. First step, I want everything to be expressed in terms of xs. That's going to mean I'm going to condition with respect to xs. Okay. So let me divide by phi of xs and xs, the condition expectation of G of xt given xs, fs, which enables me to rephrase a in terms of this phi. Okay, now everything is expressed in terms of my direct diffusion at time s. All right, I have to show that it's mixed. I mean, some technical results have got to be shown that I'm going to put under the carpet. It's globally Lipschitz, so you can make sense of the gradient applied to the random variable because Xs has a density. That's again an assumption that cannot avoid. All right, now let's do this integration by parts formula and apply the domain. Okay, so I have S multiplied stochastic integral, and I turned it to a deterministic integral, but the price to pay that I have to take the Malevin derivative of phi of S and xs. Okay. Chain rule, I can re-express it in terms of the Malevin derivative of the process. Okay. Now, what does the Malevin derivative of the process look like? So I go back to the definition and I use these two last kind of gimmicks I told you. Malevin derivative of stochastic integral, Malevin derivative of a deterministic integral. Okay, so it turns out that you can factor out this sigma. Okay, let me go back to one dimension. So I have just one Brownian motion. I'm taking the Malevin derivative in this direction. I have no choice. And I pointed out there was another term which was going outside of these two, deterministic and stochastic integral. Okay. So I can factor out sigma of u and x1 multiplied by some y process, and this y process is defined, well, just taking the standard derivative of both the diffusion and drift coefficient, remultiplying by, yes, I found, okay, I'm sorry. Let me go backwards. In time. That's a bad idea. Yeah, there is one thing, one very important thing I forgot to point out. If I look, for example, at the derivative of my deterministic integral, even though my deterministic integral is running between 0 and t, because of the fact that my process is adapted, what I have got in the right-hand side is only running between S and T, because the Malevich derivative of d alpha S of XU vanishes if S is larger, than U. That's right. So that means that you have got to have S in between those two, and the same result is holding. Okay, so now let's see. Oops. Okay, so that's why here my two stochastic and deterministic integral in the formulation of Y run from U to S. Okay, I'm left with three terms. First term, great. I can use Lebesgue differentiation theorem. Second term, well, we already have, okay, second term. No, I'm sorry. Yeah, first term, great, I can run, but okay, I'm sorry. What's going on for the second and third term, where I already pulled this straight. I have a stochastic integral of the length h, a deterministic integral of the length h. So the first term, its order is e to the 3/4. 3/2, sorry. And therefore, divide by h, it vanishes. And for the second, the third term, the last term, which I denoted by T3, it's even better, because I have two deterministic integral of an interval of length h. So that's more or less h squared. Forget it. And now, okay, I can play my favorite game, namely, look at Lebesgue differentiation theorem. Now the problem which arises is that, again, I'm unhappy with that. Why am I unhappy? I have, on one hand, the gradient, I have P of S and XS. P of S and XS was connected with G of T as the conjecture expectation. But I have the gradient. I dislike the gradient. It's exactly the way I dislike the gradient in the previous proof. So I will have to use integration by parts, because I do not want to give this gradient, keep this gradient in front of phi. So let me write two terms. One term is, okay, yeah, two terms. The first one can be rewritten kind of directly, because now I just can express the fact that phi of S and XS was the conditional expectation of xt given xs is little x, and using the density, I can express this way. For the second term, okay, here I pull the trick which I put under the carpet. I have PS, and because I have PS, I can go back to xx, expected value involving xs. But for the other term, I'm in trouble. I do not have PS. I don't have it. I force it. Okay, so let's force PS. And that's why now inside of my, outside of my bracket, I will have 1 over PS, because I've forced PS. And why did I force PS? Because again, I wanted to use the fact that phi of S and XS was some conditional expectation with respect to XS. And now I'm done, because I have everything I needed. I put everything together and I found it. Okay, how much time do I have left?
Okay, we have even 10 minutes.
Okay, so I'll just now give you a rough idea of how Haussmann and Pardoux proceeded, even though I'm not an expert at all, and to me, some part of the proof are a bit a mystery. Oh, I'm sorry. Yeah, I forgot. I'm working to rush through infinite dimensional case. Okay, so as I mentioned some time ago, we had two papers. The one was finite, the other one was infinite dimensional. So here we kind of followed the trend of what was going at that time, namely kind of particle systems. So we are focusing on each component. We have an infinite set of particles, each of it being driven by some infinite dimensional bond and motion. In a way, you can think of W of T as a trace class in a process on some kind of nice Hilbert space. Okay, so an important norm, that's the square of the gamma norm. That's just gamma is a sequence, infinite sequence gamma of beta. So it's a series of gamma beta multiplied by the square of x beta. And L2 of gamma, that's a set of x's of infinite sequences x's. So that is finite. Okay, then that's more or less natural assumption. You suppose that sigma and B are globally Lipschitz, and with linear growth in this infinite dimensional setting, the gamma beta ought to be thought of as weights, right? So we have a weighted L2 space. And once you have this, you look at the infinite dimensional sequence component-wise of stochastic interval. Each time I have, okay, here I made it clear that there was summation. It's a series. And with nice assumptions, you can prove that provided that your initial condition is lives in L2 of gamma, let's say, that is independent of your driving noise, then you have a unique strong solution which lives in L2 of gamma. So that's now it can be, with a fresh eye, it's completely standard in infinite dimensional stochastic circuits. Okay, now the problem is that we have densities. Now the trouble begins because there is no analog of the Lebesgue measure in infinite dimension. So now I am going to put some assumptions which do not have a breathtaking beauty, I agree. But we cannot the way we looked at this at the time, we couldn't help them. So here they are. All right, so we are going to suppose that we have a finite subset and that if you focus on I, Aij is going to vanish provided if J is outside some finite subset, which is defined in terms of I. Simple example, suppose that your diffusion coefficient is not diagonal, is not identity, but suppose that it's some kind of not too far away, some kind of stripe around the diagonal. And the width of this stripe can vary from one AI to I to the next. Okay. All right, now the density assumption, it's even worse. We have to make a density assumption on a finite number of components, right? Because it can only give it a meaning, at least give reasonable meaning for a set, a finite set. So what's going on? We focus on a finite subset. We look at everything which is outside and we freeze it. So we take the conditional distribution of X on this finite subset we have chosen, given everything around. And we suppose that this guy has a density. Okay. How to implement that, I don't know. And I'm really curious to see how people who are using this in AI are doing. Anyway, okay, that's more or less the density assumption. I'm not going to give much more result about that. And then we have, again, some kind of local integrability assumption. And it's just the same kind of game. We are fixing a finite set. Where is it? Okay, it's J, right? J, okay, it's written nowhere, but this capital J is a finite set. You have a finite number of compact sets. And outside of J, you just take the whole thing. And you are requiring that with respect to the law, the distribution of your infinite dimensional guy, this thing is integral. Okay. All right, now this was more or less the assumption we had in the necessary condition, right? Once you've done that, well, everything is business as usual. Your reverse process is going to be a diffusion. You are going to be telling, so suppose that this integrability condition, now I'm stating the necessary condition, right? So suppose that I have a martingale problem, I can identify the kind of infinite dimensional diffusion matrix, the infinite dimensional drift coefficients, component by component, and I encounter this kind of local integrability condition, which I denoted by 1. And now conversely, suppose that 1 holds, provided that you make slightly stronger Lipschitz conditions on your drift and diffusion coefficients. I'm not going to get into details. Then you can prove that your reverse process is a diffusion, and then your diffusion, and then your operator is defined exactly with the same components. So it's just the result that mimics what's going on in the finite dimensional case, but there is a very high price to pay for the existence of the density, right?
So in your Li condition, so big J is a subset or is a finite.
It's a finite subset, yeah.
And the G which appear in the condition is
So J, that's an index of Z. It's
for all G.
It's for all capital G.
Yeah.
And I pick a product, a finite number of compact subsets, which is indexed by this capital G, right? Okay. And outside everything.
And the condition for all small g in big G or?
It's a product for all small g and capital G.
And then the integral from 0 to 0, integral of D, so it's
good question. I think it holds for any I and J.
Okay.
Yeah, this integrability condition for also.
On G, within G and outside
Yeah.
G.
It's finite. It may depend, of course, on ing, but no, there is no, there is no hidden summation here. Okay, for any ing. Okay. All right. In fact, we have we can prove better results, but here I just made a kind of simple assumption reinforcing the Lipschitz condition I have replacing the gamma J by gamma J square. And because the gamma J, the series of the gamma J is finite, because in fact, behind there is a first class operator, the gamma J square are much smaller. And therefore, if you require an upper bound with a series of gamma J square times the square, it's much stronger than if you are requiring in terms of the gamma J. Okay, now in the last 5 minutes, let me just give you, yeah.
There was a condition on this slide. Is it for the reverse drift now, or so?
It's for the reverse. Everything is over reverse. So the claim is that provided I have all these assumptions, I said that the fact that the kind of my diffusion coefficient is kind of strip light and on the diagonal, provided that I have these conditional densities for any finite subset I have, then it behaves exactly component-wise as if it was behaving in the finite dimensional case. There is no difference. And at the end of the day, I get something here. My condition 1 is something which is very much like what I had in finite dimension, right? Except that here I have to say that I'm taking the summation of a finite set.
And the T0, is it allowed to be?
No, I am supposing, okay, all the density assumptions I've made are for T strictly positive.
Okay,
And T0 is strictly positive. So it's just kind of copy paste from what was going on in the finite dimensional setting, right? Except that it's much more cumbersome to us.
They don't need integrability until the time 0, basically, of the point. Yeah.
No, it's exactly as in the finite dimensional setting. I just need, it's a kind of local.
Yeah.
Okay. All right. So let me just give you a very vague idea of how Osman and Padu would do. So I'm just going to give you the main steps, absolutely no proof, just give you a flavor of what's going on. They're starting just the same. We have X bar is a Markov process, and we want to identify L bar and put that this holds. All right. Again, he introduces the density, no choice. But now it turns out that the density is a solution of some forward chromograph equation. Namely, that if you write it in the weak form, okay, it's kind of solution of dp over dt is L star, so LT star, that's the adjoint of LT, multiplied by pt, and of course, you can write it in a weak formulation, taking in a product with a smooth enough function. Right. Now, backward chromograph equation. The backward is something which was showing up in my proof. I have to take the condition expectation of g of xt times xs, right? Given xs. And here I'm looking at the distribution. So I fix ss. So that's just a function so that if I replace x lowercase by capital XS, I will have the condition expectation of g of xt given xs. Okay. Now it turns out that this is solving a backward chromograph equation. So it's again a PDE. The PD is different now. It's dv over ds plus ss ls, sorry, 0. And I'm given a terminal condition. That means at time t, I should have. Okay. Then prove. And that's not given. There is hard work in order to prove that. You have got to prove that, okay, I'm sorry, I should have here pointed out that the expected value of f of x as g of xt can be rewritten in this formulation, taking in a product, okay, and introducing the density and introducing the notation that v is a condition expectation. So what you want to prove, looking some algebra, now I'm putting what is x on the right and the left-hand side, and I'm focusing on the other term. And I have got to prove that, or they have got to prove that. And here it's kind of difficult part of the proof. It uses many tools, of course, the forward and backward PDs. It uses overlap spaces. It uses density. It uses many, many things. And there is one thing which, okay, I guess it's true. I'm sure it's true. But to me, it's a completely unnatural idea. They split F as a product of two functions, and they prove some identification for these two functions in terms of operators I am not going to describe. And okay, now their integrability condition. So that's more or less the question Eric was asking. They do have some local integrability conditions. So again, t0 is strictly positive. You integrate on some open subset, bounded. And here you see you require that the square of pt is the integral of this integral is it's square integrable with respect to time and space. And also, and once more, there is a guy which involves now the gradient of the density multiplied by the diffusion coefficient. It looks different from ours. I did not think deeply to see how they compare, but they have something of that flavor in it. And avoiding the density is, in my opinion, impossible. And one interesting feature is that they gave an idea of what the driving process for the reversed diffusion is, because I mean, a martingale problem, the weak solution, that's finding a pair, W bar, W hat or whatever, and the solution. So they wrote explicitly the ways this process looks like, and you might not be very happy about it because, again, it involves the density and some gradient and everything. Okay. Thank you very much.
Thank you so much. That was fantastic. Any questions?
I lost everyone.
Thank you for the talk. What did you mean with enlargement of the filtration in the beginning when you said first using?
It's okay. It's technical. Okay. Measurability is a technical issue for you. So if you could have complete. What does that mean? That they ought to contain the null sets. So you have a particular problem. You're looking for probability, and you are given your Borel sigma fields. Of course, it need not contain the p-null sets. So you add p-null sets.
Yeah, I know what.
You complete the filtration.
And that's
and
not.
I think, okay, okay. First, let me give one little more information. To be honest, I did not have a look at Haussmann, at Etienne Pardou's paper, which appeared in the lecture notes in probability. I think it was seminar de probability anyway. And there he is just focusing on enlargement of filtration. I am no specialist of that. To me, to be honest, it's some kind of thing. It's painful.
Yeah.
So I was lazy and I did not try to see how he was doing that. There are people who are, I think Etienne must be someone who at that time at least was very interested in that, unlike me.
And that's different because if you show that something is a weak solution, then sometimes you also need to enlarge the filtration to actually get the Brownian motion on the space, right?
Something like that, yeah, definitely.
Okay.
It must be something like that, even though I cannot prove.
Okay. Thanks.
Okay. Any other questions? No. So maybe there is this absolutely nice question that I would like to ask.
They are the worst.
No, it's a very simple question, right? So we identify now the diffusion coefficient for the maximum time density. And we understand that we have the weak solution there. But suppose now we know the properties of this coefficient. Suppose the mix is continuous, right? And then
I mean the reverse for the reverse. Okay.
it's somehow, although I don't know, of course, the density, but somehow I can improve, or I have the assumption that I have a ellipse brings down the ellipse diffusion coefficient, right? So therefore I have a strong.
With respect to another Brownian motion. Yes. Yeah, it's in fact,
Then my solution might say then obviously it's the same solution.
Uh-huh.
It says D.
uh-huh.
And that goes for generation, I can do whatever Brownian motion I want.
I agree,
Independent of the-
of course, of course. Okay. I am outside of my zone of comfort. My comfort zone, so I tend to say yes, of course. But mine might be completely off, but yeah, my feeling is that. And in fact, the assumptions we made for the necessary solution are more or less in the spirit of, okay, we did not claim that they are Lipschitz, but we gave some kind of integrability properties, kind of mild integrability properties.
Exactly, because you know, a prevailing assumption is that you know, that we see is that the score, as we call it, so the log of the game is Lipschitz
Mhm.
of the density, and that appears in the drift, right? So
Yep.
the base time is D, and in some sense, then I have the Lipschitz that I require for the function issue
Uh-huh.
for the generation. The one option maybe.
Yeah.
Okay, any other questions? Not before we go. Last time the speaker was fantastic.